Hello everyone, I'm Professor Ricardo. These are the lectures of classical mechanics where we will investigate the Lagrangian and Hamiltonian formalisms. But we will review the Newtonian formalism as well. Today, we will present an introduction to mechanics as a quantitative theory, an exact science. First, let me tell you that we have a playlist for the solutions of the Goldstein's classical mechanics problems, and another one for the solutions of the Sakurai's quantum mechanics problems. Help our channel, subscribing, and becoming a member. You will get access to exclusive members-only videos. Your like is also very helpful for our channel to continue helping students all over the world. So, this is an introduction to classical mechanics. Let's first discuss about qualitative versus quantitative theories. Consider a certain phenomenon. It is often possible to explain that phenomenon in several rough qualitative ways. Those explanations are qualitative theories. If we are okay with that, it may be impossible to decide which theory is correct. For instance, for a certain natural phenomenon, you may have different qualitative theories. Qualitative theory 1, 2, up to n different qualitative theories. How to say which one is the correct theory? If there are different explanations of that phenomenon, then it may be impossible to say which one is the correct explanation. Now, in contrast to the qualitative theories, there are the quantitative theories, or exact sciences. On those theories, the laws are expressed in the form of mathematical equations, which describe and predict the results of precise quantitative measurements. Physics is clearly an example of an exact science. So, what are the advantages of quantitative theories? They allow to predict and to control natural phenomena. They also allow the comparison of the results of accurate measurements with the numerical predictions of the theory. So we have experience versus theory, not in the sense that it is one or the other, but there is a comparison of the precise experimental measurements and the theoretical predictions. If a theory predicts the results of measurements to 3, 4, or even 5 significant figures, that theory can hardly be wrong. In other words, in the comparison of theory and experiment, the precision is very useful. Even when the experience and theory agrees, you may obtain a rough agreement or a close agreement. A rough agreement might be just a coincidence, but a close agreement is unlikely to be a coincidence. Probably that close agreement means that the theory is indeed the explanation of the phenomenon. In the history of science, there are many instances where small but significant discrepancies between theory and accurate measurements have led to the development of new and precise theories. Such minor discrepancies would not even have been detected if we had been satisfied with only a qualitative explanation of the phenomena. Thus, it's very clear the importance of quantitative theories. The natural phenomenon that we are interested in now is the motion of material bodies. The motion of material bodies formed the subject of the earliest research pursued by the pioneers of physics. This branch of physics, developed as an exact science, is called mechanics. You can see here an example of the world before the discovery of gravity, and gravity is part of our discussion of mechanics. As we already said, mechanics is the study of the motions of material bodies, and it may be divided into three disciplines: kinematics, dynamics, and statics. The kinematics is the study and description of the possible motions of the material bodies. The possible motions of the material bodies. The dynamics is the study of the laws which determine, among all possible motions, which motion will actually take place in any given case. Here, we introduce the concept of force. And the statics is the study of systems of forces, with particular emphasis on those which act on bodies at rest. This figure is an example of kinematics and dynamics, because we know the force acting on these bodies. And here you can see an example of bodies at rest. But mechanics may be also classified by the physical system to be studied: a single particle, a system of particles, where rigid body is a special case, and continuous media, solids, fluids, strings, etc. Here, the matter is continuously distributed in space and characterized by its density instead of its mass, which is the case in single and system of particles. Domains of mechanics. Since the last century, we must distinguish between classical mechanics and quantum mechanics. Classical mechanics describes the motion at the macroscopic domain based on our human experience, and quantum mechanics is the description of the motion at the microscopic domain. Consider this diagram, where the horizontal axis is the scale, pointing to small objects, and the vertical axis is the velocity. Classical mechanics describes the motion of not so small objects and not so fast motions, again, based on our everyday experiences. Objects that travel very fast are described by the relativistic mechanics. Objects that are very small are described by quantum mechanics. And objects that are both very fast and very small are described by the relativistic quantum mechanics or the quantum field theory. Typically, classical mechanics is a term which also includes the special theory of relativity, as is the case in many relevant references, such as Goldstein, Shaw, Taylor, Marion, and Nivaldo Lemos, in both Portuguese and English editions. Let me tell you again that we have a playlist for the solutions of the Goldstein classical mechanics, explaining the problems in detail. Take a look and let me know if it is helpful to you. Formalisms of mechanics. You are probably already familiar with the Newtonian formalism. But we also have two other main formalisms, the Lagrangian and the Hamiltonian. These lectures are focused on these two formalisms, which are extremely important and useful not only for classical mechanics, but also, for instance, for quantum mechanics and quantum field theory. In these lectures, we will also review the Newtonian formalism, which is based on the force, and this is the differential equation we need to deal with. It is clearly a vector-based formalism. The Lagrangian and the Hamiltonian are the mechanical functions of each formalism. Let me emphasize here that they are scalar functions. And these are their differential equations, the Euler-Lagrange equations and the canonical Hamilton's equations. This is a joke I found on the web used to show the power of the Lagrangian and the Hamiltonian formalism, the Lagrange's equations and the Hamilton's equations. Before we move on, I'll tell you that in classical mechanics, there are a number of fundamental physical concepts such as space, time, simultaneity, mass, and force, which will not be analyzed critically here. They will be assumed as undefined terms whose meanings are familiar to the reader. It is worth mentioning that the precise discussion of some of those concepts, for instance, space, time, simultaneity, led to the development of the theory of relativity. So let's start the study of the mechanics of a particle as a review of the Newtonian mechanics. But before that, we need to talk about index notation or tensor notation, which will be used extensively in our lectures. Let's move on.